So today we are going to go through this exam. Okay, it is October, November 2024, the variant 51. Okay.
Okay.
Now let me show it to you. So this what it says. A thin cylindrical bar magnet of length L and cross-sectional area is attached to a block. So this is the bar magnet. It got a length of L and a cross-sectional area of A. An identical magnet is attached to a trolley. And this is the block, this is the trolley, and this is the two magnets as shown. And he's showing us on the sketch a distance D, okay, and another distance S. So the distance S, can you see it, D?
Yes, I can.
Okay, it is the distance between the two edges of the bar magnets, right?
Yes.
And the distance D is the distance between one of the side, the far side of the bar magnet, and a point B, right?
Yes.
Okay, now the trolley is held so that the separation of the end poles of the two magnets is S. Okay, point B is a distance D from the north pole of the magnet on the stationary trolley. Okay, we know D, we know S and D. The trolley is released. The speed V of the trolley at point B is determined using one light gate. This is important. It is suggested that V is related to S by the relation, and here are given this relation. Okay?
Okay.
Okay. Where B is the magnetic flux, density of one of the M the mass of the trolley, K and Q are constants, right?
Yes.
Okay, so he's telling us plan a laboratory experiment to test the relationship between V and S. This is one crucial information, right?
Yes.
Okay, so from this statement, can we decide which one is the dependent and which one is the independent? From all
Okay,
these,
can you go up?
up here or up where?
Yes, here.
Okay.
D, it is the independent
Why did you decide for D?
because it can be easily changed.
Yes, but not everything that is easily changed is. We know which one is the dependent and which one is the independent from here, D.
Okay, it is either S or V.
Okay, it is from here, right? Because we need
Yes.
to plan an experiment to test the relationship between V and D, V and S, right?
Yes.
So one of them is we are going to fix, okay, or set as we need, and the other one we are going to measure, right?
Yes.
So it is V and S. So we have V and have S. So which one you are going to decide to go for the dependent and which one is the independent?
V, it is the independent. It is the dependent.
The V is the dependent, right? S is the independent.
Yes.
Okay. Can you see how the experiment goes? We have two magnets. We have two magnets. One is fixed and one is on a trolley, right?
Yes.
Okay. And both magnets, both are facing the same pole. So it is north and north. So are they attracting or are they repelling?
Repelling.
They are repelling, right?
Yes.
So you could see if we are trying to move it closer, the stronger the repulsion is, right?
Yes.
Okay. Now, if we fix it like this, we fix a distance S. We brought them to, for example, they are 5 centimeter apart. Okay. Now, if we release this trolley, what is going to happen?
The S will increase.
Yes, S is going to happen. This is going to, right? The trolley is going to do what?
Mister, I can't hear you.
You missed the sound. You cannot. Can you hear me now?
Now I can.
What about now, Dean?
Yes, I can.
Okay, now you can hear me, right? Okay. So we are saying that we have now this trolley. It is some distance away, some distance away from the other. If we release it, what would happen?
They will repel.
Yes, they are going to repel. But what is going to happen to this? This one is fixed, right?
Yes.
So what is going to
They will
happen? To the
collide.
trolley? Sorry?
Collide.
Why collide? They are repelling.
So it will move back.
It's going to move back, right? It's going to
Yes.
move backwards. Okay. Now, if we make S smaller, even smaller, okay, what would happen to the velocity?
The velocity of going backward, it will increase.
Increase, right? Because now they are repelling even stronger, right?
Yes.
Okay. Then this is what this is all the experiment about, to vary the distance S and to measure the velocity at this point. Okay? As
Okay.
we decrease the distance or the separation, the velocity is going to increase. Right?
Right.
Okay. So S is the independent, V is the dependent. How do we know that? Typically, he's telling us we are going to investigate the relationship between this parameter and that parameter. Typically, you're going to use a similar statement like this. So one of them is going to be the dependent, one is the independent. Okay? The easiest to control and to fix is going to be the independent. The one that we are going to subsequently measure is going to be the dependent. Okay?
Constant.
Constants, right? From where are we going to get these constants?
From the equation.
When we do the graph plot and we do further investigation, we are going to see that they are going to be related to the grade and intercept. We just say that they are measured, calculated
From the graph.
quantities. We just leave them like this. Then what else do we have? We have
M, which is the
MD,
mass.
MD, right? D,
We
MD,
have B.
A and B, A, MD, A, B, and L, right?
Yes.
Okay. Now the mass of trolley, right? M is the mass of the trolley. I think so.
Yes, it is a mass.
The mass of the trolley, right? D
Yes.
is the distance D. Distance. A is the cross-sectional area. B, magnetic flux, right?
Magnetic flux.
L, length of magnet, right?
Yes.
So how we are going to answer this question? We are going to make a sketch to tell him what else do we need. Do you remember he told us something about a light gate? Do you know what a light gate is?
Not really.
Not really. Okay, simple. Okay, light gate is typically something we use it to time motion. Okay, so how does it work? It looks like this. Okay, and there is a laser light. It is like a square. I don't know how to draw it, but it's something like this. And there is a laser light. Okay, if you cross this light, if you cross it, okay, the light gate will give the crossing time. Okay?
Okay.
Okay, so it is something, imagine it as a something like that looks like this. This is an opening, okay? This is opened. And we have a laser light that is going like this. If something cross this laser line, okay, the light gate will tell us for how long this thing took time to cross, okay?
Okay.
Okay. Now, this is how we do the timing. So we have this, okay, and we have the trolley, and we have a bar magnet. Okay? Then how do we set the light gate? It is set like this at this point, at point B. Okay? What do
Okay.
we allow it to cross? We allow, for example, the length of the trolley to cross. We allow the trolley to go through the light gate. Can you imagine that, Dean?
Yes, I can.
Okay. So we allow the whole trolley to go through the light gate. As it goes through the light gate, it is going to block the laser light. Okay?
Okay.
Are you following?
Yes, I am.
So what is going the light gate to give us? Crossing
Time.
time. So how we can calculate the velocity from the crossing time?
It is distance divided by time.
Yes, but what distance now?
Distance from P to the trolley.
No. Try to imagine it again. We need to
Okay,
calculate
distance
the
from the start.
velocity of the trolley, right?
Yes.
What is the crossing time? What did cross the light gate?
The trolley.
The trolley, right?
Yes.
Okay. What is the distance moved while the trolley was crossing the light gate?
The distance from the beginning of the light gate to the end of it.
No. The length of the trolley.
Okay.
Right?
Yes.
Length of trolley is L, for example. Right? So when this side of the trolley went through the light gate, the light was blocked, right?
Yes.
And it didn't come back again till the whole trolley moved through the light gate, right?
Right.
Okay. So the light gate is going to tell us how long did it take the trolley to cross. For example, 2 seconds. Okay.
Okay.
So the
Okay.
velocity at this point, is L divided S,
Crossing time.
the crossing time. So do you know now how to use a light gate?
Yes, I do.
Okay, good. I think if on the first chapters of the mechanics, they are telling you something about the light gate and how to use them to time the motion. Okay, just go and have a look at them.
Okay.
In the first 2 chapters in mechanics or something like this, he's going to tell us how to use a light gate. So let us make a sketch for how our setup is going to look like. Okay, this is the fixed part. Here is our magnet. Here is the trolley. Okay. Now tell me, Dean, we are going to change S, right?
Right.
Okay. So each time we change S and we measure V, right?
Yes, we do.
Okay. What about D? Does D changes or we keep fixed?
It changes.
But if it changes, it is going to be one more variable that is changing in our relation, and this is going to complicate our analysis. What do you think?
We can change P with it so they would cancel each other.
Yes. So P is actually not fixed, right?
Yes.
So we always make sure that the point B is a distance D away from this. Okay?
Okay.
So one time it was here. The next time when we brought them closer together, P was here. Such that the distance is always D. Okay?
Okay.
Okay. Now I understand everything. Now let us start answering the question. So how do we go through answering the question? We try to tell him
Start
exactly
from the
how we are going to
constant.
calculate. Sorry?
Start from the constant.
Yes, we are going to tell him the values that we are going to measure, right?
Yes.
Okay. We can tell him set up the experiment as shown in the diagram. Okay. 2, using a digital balance. What are we going to use the digital balance for?
To weigh the mass.
Measure the mass M of the trolley. Okay. Try to make the emphasize the quantity you are measuring. Okay.
Okay.
Using a meter ruler, measure the length.
D.
Sorry, they measure the length
Okay.
L of the magnet. Okay.
Okay.
Using, we can use the meter ruler to measure the dimensions of the cross-sectional surface of the magnet, but typically the magnets are small, so a good choice of instrument would be a vernier caliper. Okay.
Okay.
How does the magnet look like? Is it a cylinder or is it what? A thin cylindrical. Okay, this is important. So it looks like a cylinder, right?
Yes.
Okay. So use it to measure the diameter of the magnet. Is that enough?
No, I should
What?
try the formula.
Yes. Calculate the cross sectional area A as A is equal. What is it going to be, Dean?
By R square
Pi R square or pi D square over
over
4.
4.
Okay, pi D square over 4. Dean, can you give me 5 minutes? I'll be back. Okay.
Okay.
Okay. Okay, I hear Dean.
Yes.
Okay, so we measure the diameter. We are going to calculate the cross sectional as pi D square over 4. Are we okay?
Yes, we are.
Okay. What else do we need to do from our list?
Measure the magnetic flux.
What instrument do we typically use?
A Hall probe.
Okay. Use a Hall or strength magnetic flux. Okay. What else do we need to say over here? So almost everything we got. We are not measuring the distance D because this is going to come later, right?
Right.
Okay. So what else do we need to tell him? We did that. We did that. We did that. We did that. What should we tell him here?
We should tell him that each of these we should measure it twice and find the average, and we should
Yes.
keep them constant.
Okay. Take 2 readings for each value of A, B, and L, and use the average for further calculation. Keep them fixed through the whole investigation. Are we good?
Yes.
Okay, 7. Fix. Okay. Now we tell him measure the distance or the length. Actually, instead of using the length of the trolley, we can use the length of we actually ask to, since we have the bar magnet, we know the length of the bar magnet, right?
Yes.
Okay. Okay, no, let us do it like this. No. Length L of the trolley
Using meter ruler.
using a meter ruler. Okay. Using a meter ruler. But we need to tell him what we're going to use it for. This will be used to measure the velocity V of the trolley at point B with the help of the light
Time.
gate. The
Okay.
light gate gives us the crossing time of the trolley. Okay?
Okay.
Okay. We can say that V is equal, is equal L divide crossing
Time.
time. Okay. Now we go set the distance S between the two magnets and change the position of point B such that it is a distance D from the north pole of the trolley magnet. Okay? Right?
Okay.
Okay. Take different sets of values for S and V. Make sure that that point B is always at a distance D
From
from
the North Pole.
the North Pole. Okay, now I think we have done everything that we need to set and measure and everything. Okay, then tabulate your finding in the table below. Okay. So what are going to have in the table? What do you think?
We'll start from the independent.
Yes. What is it going to be?
It is S.
It is S, right? So we said that in the table we are going to have S, right?
Yes.
And we're going to keep the units in meter. It can be in centimeter, yes, it should be fine. But let us keep it in meters. This is the standard. Okay?
Okay.
What else do we need in the table?
We need the V.
V, right? And what are the units for V?
Meter per second.
Meter per second, right. What else? Or are we good?
Then we will make Y equal mx plus c to find.
So here is my equation, Dean, right?
Yes.
This is my equation. Does it look like one of a straight line?
No, it doesn't.
I need to change, to manipulate it a little bit to make it look like a straight line, right?
Yes.
Okay, so what we are going to try to do, keep the dependent in one side and the independent on the other side, right?
Right.
So what is the dependent here? Where is the
Dependent,
dependent?
it is the V.
The V, right?
Yes.
Okay, so we need to move the whole of M over 2D to the other side, right?
Right.
Can you help me do that?
Okay. V square equal
Okay.
KA square B square L square to
KA
2D.
square, B square, L square, okay.
2D
2D, yes,
over
over.
S4.
Okay, I'm going to write it a little bit different. I'm going to say M and 1 over S4 like this. But it is the same, right?
Yes, it is.
This just makes things looks easier for me. What about this? Are we done or
Minus Q.
minus?
Q.
Only minus Q? Remember, we are multiplying this one, this side, by the whole of this thing.
Okay. Minus
2QD over
M.
M. Now, can we make a plot of V versus S?
Yes, we 1 over S.
Is it 1 over S?
Yeah, 1 over S4. Yes.
1 over S to the power 4, right?
Yes.
And what about here? Is it going to be only V or something else?
It's going to be V square.
V square, right. So over here, we need 1 over S4, right? What are the unit of 1 over S4?
Meter minus 4.
Meter minus 4, right. What about here?
V square.
V square, the units.
Meter square per second square.
Yes, exactly. So now we tell him, make a graph plot of 1 over S to the power 4 on the x-axis and V square on the y-axis. a straight line is expected. Right?
Yes.
Then we one over s to the 4 meter minus 4 v square meter second square, right?
Yes.
Right. Now the gradient
Is used to measure the constant.
Yes. Now what is the gradient going to be?
K square B square L square 2D over M.
Yes, exactly. So we write it as gradient is equal to 2d k a square b square l square divide m, right?
Yes.
Okay. What is the intercept?
Minus 2QD over M.
Minus 2qd over m, right? Okay. Now he is asked to calculate k and d. Therefore, k is equal to what?
M multiply gradient.
M times gradient.
Divide by 2D A square B square L square.
2d a square b square l square, exactly. What about the q?
Q equal M multiply the intercept.
Minus
Minus M
m times
multiply
intercept
intercept divide 2D.
2d. Okay, good. Now we tell him the last thing we do,
Safety precaution.
any safety precaution to be taken or whatsoever. Okay, there's nothing clear over here, but caution should be taken when handling the magnet, something like this. Okay.
Okay.
Okay. Do you have any questions over here?
No.
So do you know how now we proceed to answer this question?
Yes, I do.
Okay. We need to decide which one is going to be the dependent and which one is the independent. He is typically asking a guide from this statement. Okay. Then he's telling us which values or which parameters that we can calculate. Okay. All any other parameters, we need to tell him how we are going to measure, right?
Right.
Okay. Then we always try to manipulate our equation such that it looks like that of a straight line. Okay.
Okay.
Are we good?
Yes.
Okay. Now let us go to the next one. A student investigates an electrical circuit. A power supply of electromotive force ES and negligible internal resistance is connected in series to 3 resistors, each of resistance Z. Do you know what are the units of electromotive force?
V
Sorry?
volts.
Volts. So if we have a battery, we call the voltage across the battery electromotive force. Okay? A cell, okay. A cell, an ammeter, and a resistors of resistance R are connected in parallel across one of these resistors. So we have this setup. We have a battery, resistance, and ammeter. Okay. The current I is measured by the ammeter for different values of R. So he is varying what?
What?
So he's telling us the current I is measured by the ammeter for different values of R. Can we decide which one is the independent and which one is the dependent?
Okay. R is the independent.
Independent. I?
And I is the dependent.
Exactly. Now, if we take a look at this equation, does it look like a standard straight line equation?
No.
No. What we need to do?
We need to make I in one side.
Yes. The dependent in one side and the independent on one side. So what do you recommend? How should I rewrite this?
Okay, we can say I equal
equal
3E minus ES
ES. Okay.
divide by 3R plus 2Z.
2Z, right. Are we good now?
No,
No. Why?
because the R is not in separate. So we can
Yes,
say
it's
1
not
over
separate and we
3R.
cannot write it in a standard form. So he's giving us kindly a hint. So he's telling us a graph plot is plotted of 1 over I on the y-axis and R on the x-axis. So what should we else do to this equation?
I can say 1 over I.
1 over I. Yes. What are we going to do to this side?
I want to find the gradient.
No, we are not yet there. We are not yet there. You invert it. We said this is 1 over I, right?
Yes.
So you invert it, right?
Yes.
So we need to do the same here.
So say 1 over 3R plus 2Z.
What?
You said I invert it here, then I should invert where?
Yes.
Where should I invert?
Everything. This whole thing.
So it will be 1 over 3R.
No. It's going to be like this: 3R plus 2Z divide 3E minus ES. We are just inverting it, right?
Okay, yes.
So if we have F is equal A plus B divides CO plus D, right? If we invert F, it's going to be simply C plus D by A plus B, right?
Yes.
Okay. Now, can we separate the independent variable from anything else?
Yes.
Okay. How we do that?
I will say 3R
Okay.
plus 2Z over 3E minus 3S.
Not exactly. Because now this divide everything over here, right?
Yes.
So let us separate them. What else do I have here?
3e minus
3.
3s.
Yes. Okay. Now this can look a little bit like that of an equation of a straight line. Why? If I can rewrite it like this. Does it look like now that of a straight line?
Yes.
Okay. So what is the gradient now?
3 over 3e minus 3s.
Yes. And what is the intercept?
2z over 3e minus 3s.
Exactly. Okay. Let us proceed. Now we have R, we have I, and we need 1 over A, 1 over I, right? Right, Dean?
Right.
Okay. And he's telling us includes the absolute uncertainty in I.
Okay.
Right? So simply I just let me get the calculator. So
Mister, I will change 194 because it is in microampere.
let me see how he's going to do that. Okay. We need to change it to amps, right? What is micro?
It is times 10 to the power negative 6.
Yes, 10 to the power minus 6. Okay. Okay, good. Just let us first calculate one of them. So it is 194 minus, okay, right? Can you see it on the screen, Dean?
Yes, I can.
5.154 times 10 to the power minus 3, right? But
Yes.
remember, we are getting 1 over microamp. So when the micro goes up, what is going to do?
It will become to the power 6.
To the power 6. So this 5154, 10 to the 6. 10 to the 3, sorry. Oh, no, not even this. Sorry. Going to be 5.154 times 10 to the power minus 3 plus 6 times 10 to the power minus 3, right? And 5,
So it
4.
will be 10 to the power 3.
Is that okay?
Yes.
Okay. 5, 1, 5, 4. Okay. Now we need to calculate the absolute uncertainty. How do we do that?
Okay, we will find the maximum minus the average.
Not really. Do it like this, Dean. It is an equation, right?
Yes.
So f, it is the function that we need over here, right? We call it f. All right? Is equal to what?
1 over I.
1 over I, right? So we
Yes.
have f is equal. So what is delta f?
Change
Delta I.
over I
Yes. Times what?
time 1.
Times f.
Okay, yes.
Right? Delta f over f is equal delta
Yes.
I over I. So we say delta f is equal delta I divide I times f. Right? What is f?
Yes. F, it is 5.
No. What is f itself? What is how it is related to I?
It is 1 over I.
So simply delta f is delta I divide I square. Okay? So the absolute uncertainty is going to be delta I divide I square. Are you following?
Delta I divided by. Okay. Okay,
So we
yes.
got it from here, right?
Yes.
Okay. So now we say delta I is 2. Right?
Yes.
Okay. Divide I square.
By 5154 square.
Okay. So it is going to be 2 divide 194 square.
Okay.
Okay. Now we check just the units. So this is going to be microamp divide 194 microamp square. Right? Are you following me?
Yes, I am.
1 microamp is going to be going with a microamp. So what are we left?
Okay.
Okay, amps to make the units compatible. Now let us do the calculation. We have 2. Sorry, this is square. We have 2 divide 194 square, right? Right, Dean?
Multiplied by 10 to the power 6.
10 to the power 6. So what are we going to get?
53.
53. But typically, we are going to keep it only to one significant figure, right?
Yes.
Okay. So we how do we round this up?
50.
50. Okay. Okay?
Okay.
Okay. Good. Sometimes you might need to change. Okay. Sometimes some people might change this 4 to, because this is got, you see it is 50. Okay. To one significant figure, right?
Yes.
Okay. So sometimes we can just change this to 0. But we are not going to do that. Okay, Dean?
Okay.
Can you do the other one for me?
Yes, I can.
This one? Okay, do it for me,
Okay.
please.
The second one, it is also 61.7, so 60.
Sorry?
Okay, one
No.
second.
What is 1 over I?
So 1 over 180, it is 5.55 multiplied 10 to the power -3.
Mm-hmm.
So it is 5.555.
5,555, right?
55. Yes.
Okay, and what is the uncertainty?
60.
60, exactly. Good. What is this 172?
It is 5814.
5184. 5158.
5814.
5814. And what is the uncertainty?
It is 70.
70. Good. Let me do those two for you. 6250, right? $6,666. Are we good?
Yes.
Can you do the last one for me?
Okay. It is 6944.
And what is the uncertainty?
It is 100.
100, exactly. Okay. We are good. Now we go and try to do what? Our graph plot, right?
Right.
So, Deem, can you help me now?
Yes.
Okay, we got 1.5, right? So, where is 1.5?
It is in the 6 from 140.
Sorry?
It is 6 square from 140.
Why 6? It is the fifth, right? This is 0.1.
Yes, yes.
Okay, so 1.5 should be around here.
Yes.
Sorry, this is 0.2. So 1.5 is over here, right? What about 5,154? How to do that?
They are separated by 2
Where?
by 20, right?
By
So it is
200.
7.
Sorry?
It is 7.
7?
7 squares, yes.
Why?
I wrote 5154 minus 5,000 divided by 20.
Ah, you are doing it for the y-axis. Sorry, okay. Okay. So what we did, 5154, right?
Yes.
Minus
5,000.
5,000, right? Divide?
20.
No. This is 5,000 or 5,200.
So So it is 200.
Divide 200, right?
Okay, it is still 7.
Yes, you got 7, but it is 0.7. 5154 minus 5,000 divide 200. It is 0.7, between 0.7 and 0.8, right?
Yes.
5, 6, 7. This is 8. So it is something over here, right? Are we good?
Yes.
Okay. What about the error bars? So we have 50, right?
Yes. 50
Divide
divided
200.
200.
So what do we get?
0.25.
550 divide 200. 0.25. Meaning what?
2 above and 2 below.
2.5. So this should be 1, 2, right? And somewhere here.
Yes.
Okay. Then this is 1, 2, okay, and somewhere around here.
Yes.
Okay.
Okay.
Is that okay?
Okay.
Now, the other one, 1.75.
It is 1. It
Where
is 7.5 step from 1.60.
7
and half steps from 1.
7.5 step, right? Is
Yes.
it? Let me check it. 0.15 divide 1. Yes. It's 5, 6, 7 between here and here, right?
Yes, it is in the middle.
And
Yes, right.
5,500. So
It is 7 steps from 540.
7 steps. 5,
From
6,
5.
7, right?
Yes,
Is it here, over here?
right.
Okay, I will just trust you. Now, what about the 60?
60 divide 200.
Yes.
It
What do we
is
get?
3. 0.3.
0.3, right?
Yes.
So meaning what? 3 steps.
3 steps above and 3 steps
1,
below.
2, 3. Almost here. We count down. 1, 2, and 3. And we draw a straight line,
Yes.
right? Okay, good. We are doing fine. 1.92.
It is 6 steps from 180.
Yes. And 5814. What is it? This one?
1 second. It is 7 steps from 800.
Is it?
Yeah,
How many?
7 steps.
Can you check again?
Yes, it is
What did you get?
I got 0.07.
0.07. 0.07, right?
Yes.
Okay, so we look to the number immediately after the decimal point.
So it is 1?
1. We are just rounded to 1, right?
Okay.
Okay, so it's almost there. Okay?
Okay.
Don't get lost here. What about the 70?
70 divided 200,
Okay.
which is 0.35.
0.35. Right? So we
Yes.
count 1, 2, 3, and a little
And a
bit over
half.
here, right? Then we count from here. It is 1, 2, 3, okay, and a little bit over here. We can never be very sharp, right?
Yes.
But we are close enough. What about 2.22?
It is 1 step from 2.20.
Yes. And 6250. This is 6.22, right? Or 2.22, right?
It is 2.5 steps from 6 to 100.
2.5 steps, right?
Yes.
1, 2.5, right? Over here.
Yes.
Okay. What about the error bar? 80.
80 divided 200. It is 0.4. So 4 steps.
0.4, right? So we count
Yes.
up 1, 2, 3, 4. We count down 1, 2, 3, 4.
Yes.
And we do the straight line. Okay?
Okay.
Okay. I think our time is running up for this. Okay, we come back in 10 minutes. I will do the remaining 2 and you do the same.
Okay.
Okay? Okay, see you in 10 minutes.
Okay, see you.
Okay, so this is what I got. Those 2 data points. Okay?
Yes.
Now, what else do we need to do?
We need to make the line of best fit.
Line of best fit. Okay? So, how do we decide that the line is one of the best fit?
It covers most of the points.
Not only that, we try to make it pass through the center of most of the points. Okay?
Yes.
Okay. Let me see if I can do one. Think this might be my line of best fit. Okay?
Okay.
As close as the centers. For the other one, I would use a dash line to make it easier for me to recognize which one is the best fit. Let me bring that. Okay, so can you see my worst fit line?
Yes, I can.
Okay, now we are going for the slope or the gradient. So we draw two squares, right? Or right angle triangles. Write them. Write them.
Okay.
Okay. We make two right angle triangles.
Yes.
Example, this one. And the other. Like this. Are we good?
Yes.
Okay. So for me, just to be consistent with what I have, my best fit line came to have a slope of 6800 minus 5600, 2.6 minus 1.76. And I got 1428.6. The worst fit line, I got 6740 minus 5600 divide 2.6 minus 1.78. I got 1390.24. Okay. Can you
Okay.
get the unit for the
Uncertainty.
gradient? The gradient
It
unit.
is A inverse
Yes.
ber ber K ohm.
Over R ohm. K, yes, kilo ohm. Yes, okay. So it is A inverse, A minus, right? And kilo ohm minus 1, right?
Inverse. Yes.
Okay. So this is the best fit. How we calculate uncertainty?
What did you say?
How we can calculate the absolute uncertainty in gradient?
Okay, it is the worst fit minus the best fit.
Yes. 1428.6 minus 1390.24. Right?
Yes.
Comes it?
Mister,
Yes.
okay, your voice wasn't clear.
Sorry?
Your voice wasn't clear.
Okay. So 1428.6 minus 1390, sorry, 24, right? 38.36. We keep it to one significant figure, right?
Right, so it is 40.
40. Now we are going to write the
It is
1428. And we keep it
zero,
same of decimal places. Okay, Dean?
what?
We keep it to the same number of decimal places as the absolute uncertainty, right?
Yes.
Okay. So A minus 1, kilo ohm, right?
Right.
Is that okay with you?
Yes, it is.
Okay. So determine the intercept and include the absolute. How should we proceed?
We will write y equal mx plus c. Then
Y
we
is
will
equal.
find 2 points
See, and we find 2 data points.
from,
One, the best fit.
from the best fit and from
And
the worst fit.
okay. So these are the values I got. Okay. Those are the 2 values I got. Now we
Okay.
substitute.
Then you, yes, yes,
Yes,
the
can you help
gradient
me?
of the best fit.
Can you help me?
Yes,
So C is equal Y minus MX, right?
yes.
Okay, now help me.
So 6/400
Yes.
minus the gradient of the best fit.
The gradient of the best fit, it is 1428. 1142 actually, right? If we round it up. One four two nine.
Yes.
What is
Multiply 2.32.
okay? I got 3028.
Okay. Then we will do the same thing for the worst fit.
We do the same for the worst fit.
6/400
And what is the
minus
worst fit gradient?
1390. 1390.
1390, yes. And what is the point X?
2.36.
Yes. I got 3120. What is the units? What are the units?
A inverse.
A inverse. Good. Absolute uncertainty?
It is difference between the worst fit and the best fit.
Yes. So it is not 28, it is 82, sorry. Okay?
Okay.
Now using your answer, determine the value of E and Z. Include appropriate units. Okay. Now we need to go back. Gradient is 3 divide 3E minus ES, right?
Yes.
So we have the gradient is equal minus ES. Okay?
Yes.
And we have the intercept.
Minus ES.
Okay. Now we say that we are asking for E, right?
Yes. In the first one, we want E.
Are we okay?
Still, we want
Sorry?
to make E the subject.
We need E, right?
Yes.
Okay.
So it will be
Is that okay?
yes.
Okay. Are we good?
Yes.
Okay.
What about the E that was in front? What about the 3 that was in front of the E?
We divide it. Here it is.
Okay.
Right? It was
Okay.
3E, right? And we got 3 over gradient, right? And we got ES, right?
Yes.
Okay. Then we divide the whole thing by 3.
Okay.
Okay. Let us substitute. What is the gradient? What is the
The
gradient?
gradient, it was 1429.
1429. Okay. Now we have to be a little bit cautious, Deem. Remember, we have kilo ohms.
Yes.
Okay? Divide kilo ohm. So actually the gradient is going to be 1.429.
Okay.
Right? So
Yes.
1.429 plus what is ES? We have it, right?
Yes. 2.20.
Divide 3. And we calculate. What do we get? This value.
Okay.
Okay?
Okay.
What about Z?
It is 3e minus es multiply intercept over 2.
Yes. Now we substitute. What is 3E? What is ES?
2.20.
What is the intercept?
3082.
Sorry? 3082. Okay.
Divide by 2.
Yes. I get something like 3230.7. And now use. Okay?
Okay.
Okay. Or 3.23 kilo ohm, as you wish.
Okay.
Okay? Determine the absolute uncertainty in E. So we need E, right?
Yes.
So what is E? E is equal, this is
1 over gradient plus es over 3.
ES over 3, right?
Yes.
So if we have a function which is A plus B, so what is delta F?
Delta A over
Yeah.
A?
No?
No, delta A plus delta B.
Yes. So we do for this one alone, independent, and this independent, then we add them, right?
Okay.
So what if the function is 1 over gradient? Remember, we did something similar, right?
Yes.
What did we do?
We just did Delta gradient over gradient.
Delta gradient over gradient. Not exactly. Remember 1 over I, D?
Yes, I do.
Okay, it was delta F is equal 1 over gradient square, right?
Yes.
So delta gradient divide gradient square. Remember when we did it for the 1 over I, right? One over the function.
Yes.
Okay. So it is delta gradient divide gradient square plus this one.
Delta ES over ES.
No. It is just ES, right?
Yes.
Over 3. Right?
Okay.
Okay. So we did this alone, independent, then we add them together. Okay? Do we know what is delta gradient?
Yes, we do.
It was 40, right?
Yes.
1,4. Was it 1,432 or
1429.
1,429? Square, right?
Yes.
Plus delta ES, we know it. It is given.
0.05.
Okay? We do the math and we get something like 0.036.
So it is 0.04.
0.04. Okay? And E is 1.43. We keep to the same number of decimal places, right? How many decimal places we have?
We have 3 right now.
Here we have 2 decimal places, right?
Okay.
So we keep it
Yes.
2 decimal places. Volts. Are we okay? Now, do you have any question for now?
No, I don't.
Okay. Now, final question. The experiment is repeated. Determine the resistance R that gives a value of I of 250 microamps. Okay. Now we go back to the equation, right? This is our equation. We rewrite it. Okay. As R function of the equation. Okay.
Okay.
So we have, what do we have? We
This
have
one.
E minus ES is equal I times 3R plus 2Z. Right? And we need R.
Okay.
We are given I. Okay. So 3R plus 2.
So R equal 3E minus ES divided by I.
Okay.
Yes.
3 plus 2Z is equal to that. Minus 2Z. Are we okay?
Divide 3.
Divide 3. No, all what we need is just to plug in the values that we have. So do we know E?
Yes, we do.
1.44, right? What about ES?
Yes.
2.2. What is I?
250. But we will convert the unit.
Yes, -6, right?
Yes.
What is Z?
It is up.
Yes, over here. 3,250
3.270.
ohms. Right? Divide 3.
Yeah. Yes.
If we do the math, we get something like 635 ohms. So we have 635.
Okay.
Is that okay? Do you
Yes,
have
it
any
is.
questions?
No, thank you.
Okay. Then good. Try to make the calculation for the last exercise again, team, and make the
Okay.
repeat the graph and the whole calculation again, okay?
Okay.
And I will send you a recording for this session.
Okay, thank you.
Okay, cheers.
Bye.
Cheers.